SwayamPrabha. Digital India. Educated India.
Today we are going to do one more case study on the design of a probe for scanning probe microscope. So, essentially it is only the probe part of a scanning probe microscope we have selectively chosen, and we will see that how we can select the material for this type of a probe. Now, scanning probe microscopy is one of the most powerful imaging technology that is available today, and this is used for imaging of surfaces using a physical probe that actually scans the specimen by something like touching the surface with a mechanical probe. Okay. So, this is like a cantilever probe, as you can see here, and it has a sharp tip and it is going to touch. So, a material has many kind of undulations if you look at it. So, what it is going to do? It is going to touch it, and as it is touching, its deflection is changing, which is picked by the laser beam, and then from the laser beam the light that is coming to the quadrant photodiode, very highly sensitive, and from that it actually, from the deflection it actually find out that what is the nature of the surface of the sample, like this type of a surface. So, the very important tool in case of a scanning probe microscopy is actually a cantilever beam, whose end deflection is what we detect and put it as a change in the form of a laser beam position changer at the detector. The bottom surface of the probe has a sharp tip, which is just 3 to 6 micrometer tall pyramid with 15 to 40 nanometer end radius. It is very challenging. In fact, this is the part which is, you can say it like a MEMS or a NEMS device on its own, that bottom part of the system. It is a micro electromechanical or a nano electromechanical system, and naturally the deflection corresponds to the surface topography. So, our tip has to be very fine, and then whatever little deflection will be produced, that is to be interpreted in terms of the surface roughness. That is the idea for scanning probe microscopy probe. Now, what is the problem statement for us? That select material for the cantilever beam, because you see that we are doing it from the resonating frequency point of view, okay, and we have to maximize the resonating frequency. So, we have to select material for that probe. This part is very small. So, that is why is not important from the resonating frequency point of view, its contribution to resonating frequency will be very small. Now, the point is, why are we interested on the resonating frequency? It is because many times we use this probe in terms of tapping the surface. So, we tap the surface at various points. So, while tapping, suppose if it is very flexible, then its natural frequency will get actually coupled with this tapping frequency. So, that means this particular beam will start to have resonance. We want to avoid that. To avoid this, we want to keep the cantilever's natural frequency so high, something like 30 to 100 kilohertz, so that it never interferes with the scanning frequency. So, that is what is the idea, that how can we maximize the resonating frequency of the system. Now, let us go to the board and try to see that how we can do the same thing with the help of the Ashby technique. Okay. So, let us try to solve this problem. We have a cantilever beam, let us say. I just draw the beam first, and let us say that the beam is of uniform thickness, although in practice it is not like that exactly, but let us say that the beam is having uniform thickness, and one edge, this is the fixed edge of the beam, right. Suppose this is the fixed edge of the beam. The beam has the probe has a length L the probe has a width, say W, and the probe has a thickness, say this is T. Okay. And there is a tip here, but we are right now currently neglecting that, that tip effect, etc. Now, so let us write it down, that what are the objectives of our analysis. Let us try to put this thickness T, let us put this as length L. I hope it is clearer to you now, and I am applying this color, that is the length L, that is very important, and also the last parameter, that is the width of the system. Okay. Width of the beam. So, with this, now what is the objective for us? Objective is that maximize the resonating frequency of the beam. Okay. And what are the constraints for us? Well, length is of course a constraint. So, this is length, and we may put thickness also as a constraint, because if it is too thick, then it is difficult, in any solution, if you have that, it is difficult to really use this probe in terms of scanning a system. So, what is the free variable for us then? Free variable is of course material property. So, selection of material and cross sectional area. Okay, we are free to choose the cross sectional area of the system. Now, in order to know the resonating frequency, what we are going to do, see, this is a continuous system. So, as a result, for a continuous system, it is actually consisting of infinitesimal lumped masses. So, they do not have one natural frequency, but many natural frequencies. However, when I am telling the resonating frequency, we are actually implying that it is the fundamental frequency. So, this is basically nothing but the fundamental frequency, and one way to obtain this fundamental frequency is that we actually consider this omega n as square root of k, that is the stiffness, the bending stiffness, the bending mode. So, we may put it as kb over effective mass. Okay. So, corresponding to the first mode shape, which is somewhat like this, if I draw it, that is the first mode shape. If you actually excite such a system, that is the way is going to vibrate. So, between that system, the natural frequency is square root of kb over m effective. The question is, what is the kb and what is the m effective? So, how can we find it out? Okay, what is the end deflection? End deflection of a beam, of a cantilever beam, we know that it is delta equals to FL cube over 3 EI. In other words, I can write that F over delta is actually 3 EI over L cube. In fact, that is the K effective for us. Okay, is very close to the the static deflection of the system corresponding to this that stiffness. We can consider it to be a good KB for us. Okay, so we can consider this to be an effective stiffness of the system. We let us call it as the bending stiffness of the system, KB. Now we also have to know what is the M effective for the system. Now I will not go into the details, but if you look at any textbook, any textbook on mechanical vibration, you will see that for this type of case, the M effective will come out to be 33 over 140 times the mass of the beam, 33 over 140 times MB. Now the question has come for us that what is MB? MB we can write it as rho times length times W times T, right? Rho L W T, that is what is the MB, the mass of the beam. Now in this case we have to keep in mind that the cross sectional area is considered as the free variable. In other words, WT is nothing but MB over rho L, okay, and that is our WT. So if you look at the expression of omega n, so let us try to write down the expression of omega n here, and if we use the expression of omega n, let us try to now erase this part and try to work on the system. This part you already know. I am just keeping the expression of KB, okay, and the expression of W M effective, okay. Omega n here is actually as radian per second, right, and here let us put a different variable then, because we have divided by 2 pi. So let us put it as 1 over 2 pi square root over KB over M effective. So if I now work further, what we will find out is that this will become, now also we have to keep in our mind that I, which is the I of the beam, is actually W T cube divided by 12, okay. And so I can put that expression also here. So F will be 1.03 divided by 2 pi, that is the 3 square root, we have kept it out, okay. And then what is it that we have inside? Let us try to keep all the parameters now here, E, okay, and then we have from IB we are getting basically, so 3E is coming here, that is our 3E term, okay. Then we have W T cube, then we have M effective, which is 33 over 140, and MB is, I can write it as MB here, that is WT is this thing. So I can write MB as rho L times W T, right. So, 33 over 140 times MB as rho, yeah, let us just keep it as 1 for the time being. Okay. So, 1, let us keep it right now. So, however, this we need to really look into it now, that this MB itself is giving us what, rho L times WT, that is one we are getting, okay. And then that is our M effective, and what else are we getting from here? We are getting okay, 33 over 140, that is the M effective. We have the 12th term here, right. This 12th term we have to keep. So, we have the 12th term here, and also we are going to have, let us see, 3 is there, IB is WT cube, that is fine, M effective is there, yes, L cube we are missing, right. So, that is all, these are the terms that we have. Okay, great. Now, as has been already solved by this particular part, so this is coming out to be 1.03 over 2 pi. This has been solved already by our TA, and multiplied by, let us look at this part now very carefully. So, I can write this WT cube as WT times T square. Okay. So, if I write like that, then I have no problem, I am actually getting the T out, okay. And then the WT, of course, it is a free variable, but it is cancelling in this case. So, that is also fine with us, and what we are, L to the power 4 is there. So, we can actually bring L square here, T over L square, and we do not want to touch them either. And finally, we have square root of E over rho. That is the material property index. If you want to maximize this frequency, you have to maximize the square root of E by rho. That is the point that we are getting as a take home, exercise result from this system. So, let us write it down, that E over rho to the power half, if I keep a suggested minimum value for it for the design, then this will become in a log-log plot as log E equals to log rho plus 2 log C. In other words, as you can see that in a log-log plot between the two, the slope is 1, that is 45 degree. Okay. And this, depending on the value of C, we get the intercept part of the line. So, that means in the property index of log E versus log rho, the slope is unity, but it starts with some minimum value. So, that value is what we the C, once we determine the 2 log C, we will say what exactly is this value, but this is what will be the nature of the line, and that we are going to get provided we keep area as the free variable. Now, suppose we do not want to keep area as the free variable. If we want to keep, suppose anything else, suppose if thickness becomes a free variable, what happens? So, suppose there is one such system which is not a probe. In case of probe, you need that, where thickness is a free variable. Then we know that in our final expression there will be a T term, and we know also that this T we can actually replace it if we remember that mass of the beam was nothing but rho W T, okay, times the length of the beam. So, T is nothing but m b over rho w L. So, even if I take everything out, but still we have a rho term here. So, that means our constant f will be a new constant now, let us call it sometimes of constant C1, and then there is a rho term here. So, it will become 1 over rho times square root of E over rho. In other words, this will look like C1 and square root of E over rho cube. In other words, in such a case, suppose I use so this is what for us as area free variable, let us call it area, and let us just put just below this line put this new one, then this new one would look like we have f as C1 square root over E cube. So, we can write it as log of E equals to 3 log rho plus some constant, correct. You can evaluate it, but the important thing for me is that here it was unity, here it was unity, and here it is 3. That means the slope changes. This slope, which is 45 degree for us, that slope changes in the next case. So, this changes the nature of the solution. We will see that how all these things affect our choice of the material. So, the choice of essentially I want to actually impress on you that the selection of the free variable T can qualitatively, the selection of the free variable, so to say, can qualitatively change the nature of the solution, and very dramatically, very significantly. Let us go back and see that what material will you choose in such a case. This is what is our the diagram of E versus rho. As you can see, x axis is our density, y axis is our Young's modulus E, and here we have the plot of all the materials from ASBIS, material selection in mechanical design, and as you can see that this is the line that is for E by rho equals to 1, subjected to the initial values of our own choice. We will see that what are the materials that we can get. We can either get something like silicon nitrides etc., those which are above this level, or we can get something like, suppose if you want to choose something which is also equally hard, you can actually choose ceramics, you can actually choose things like diamond also here. So, which will be somewhere in the technical ceramics range, you will see that diamond also is a good solution, you can find it out. Okay, it will be somewhat higher than the silicon nitride, but silicon nitride is a cheaper solution in terms of the cost, hence that is what is actually much more preferred solution. Depending on the application, one may go for some or the other advanced versions of metallic alloys in this region, but generally it is silicon nitride which is used in this particular type of a situation. So, thus we have demonstrated again for another typical application that how you can use the ASP chart very selectively and your knowledge of materials in order to select a proper material for something which is as complex as the probe of a scanning electron microscope. So, this is where I am going to end today, and in the next lecture I am going to now cover other non mechanical properties like optical properties, electrical, magnetic and thermal properties. Thank you.